Hoy, en Toquin, Mario, Guido y Pierre Magistretti se aventuran en el tema del metabolismo energético y el cerebro.
Hello, Pierre. It's a pleasure to be with you. Thank you very much for accepting our invitation to talk about neuroscience, life, and so on. How are you doing
Very
today?
well. Actually, I very much enjoy being in this place. I think it has a lot of charm, and I will definitely come back and have a beer here later.
Oh, great. Yeah, this is a very interesting place, for sure. But your contribution in science is great on the field of brain energy. But I was wondering, when did you make the decision to become a scientist?
Well, actually, as strange as it may seem, I became very much interested and decided that I was going to study the brain when I was maybe 14 or 15 years of age. My family is in the medical field, so both my parents were MDs, but they had nothing to do with the brain. But somehow, so maybe that has kind of put me in the general topic of medicine, but I was fascinated by the brain, and so I decided that I was going to study, and in particular, by the way, by brain chemistry, biochemistry. And I remember, I remember that when I was 16 or 17, a bit later, when I had started reading about it, I thought I would study neurochemistry. I created this term, and then I was very disappointed when I found out that it existed.
Already existed.
So anyway, eventually I went to medical school. And while at medical school, I became more and more interested in psychiatry. I wanted to become a psychiatrist, but at the end of my medical school, I thought that, before becoming a psychiatrist, I had to know how the brain worked. I thought cardiologists, they know how the heart works. So I had to do the same. So, and at that time, at least, neuroscience during medical school was taught. There is some neurophysiology, some neuroanatomy, but there was not real neuroscience as of today. So I decided to go on and got a PhD from University of California, San Diego. My medical degree was from University of Geneva in Switzerland. And then I came back to Switzerland. Things were going well in terms of science. So I stayed with neuroscience, and as I like to say now, 35 years later, I'm not a psychiatrist, and I still don't know how the brain works. So it's not really a great success, but anyway, I had a lot of fun and so far and excitement in doing what I am.
Tell us, please, about brain energy, metabolism, and feeding and food intake, and what happens when children are very well or not very well provided with food, what happens with the brain, what happens with the energy needed for the brain to function, to work properly.
Yes, I mean the connection between brain function and energy metabolism is really been the key question that I've studied over 30 years. In other words, how the electrochemical events that are at the basis of neuronal function, synaptic potentials and all the signaling, how this is coupled to the delivery of energy, in particular, when needed and where needed. Because there is something quite remarkable, I mean, since Sherrington, in a way, and then later the work of Lou Sokolov, had shown that there is a tight coupling between neuronal activity and energy metabolism and even vascular flow. I mean, the liver.
Okay. As I mentioned earlier, your great contribution about brain energy metabolism was used for the imaging and for all the studies involving imaging in living cells, organs, and human beings. Can you tell us about that?
Yes, indeed. Actually, by studying the role of these cells that couple neuronal activity to the delivery of energy to the brain locally, it became clear that this could be a mechanism that would provide an explanation to the origins of the signals that are detected with these functional brain imaging techniques. Everybody has seen these images of the brain where you have red areas, blue, yellow, showing activation of the brain. And for example, when I move my left hand, the one part of my brain, the cortex, in the motor part of the cortex, is using more energy than the rest of the brain. It's like a muscle. When the muscle is active, it uses more energy. Mm-hmm. Well, for neurons, it's the same. When they're active, they need more energy. And so by showing that there are these cells that detect when neurons are active and where they are active and when, and then deliver more energy, glucose, sugar essentially, and oxygen, you will provide this coupling. And what is interesting is that all the imaging techniques that are used do not detect directly electrical activity of the brain, but they actually detect the consumption of glucose, of sugar. They detect the utilization of oxygen, and they detect the blood flow. So what these techniques that allow to visualize brain at work detect actually metabolism.
So you can see in a brain that is activated in response to a nice or a pleasant situation, or in a situation in which there is a risk, activations of special areas, special metabolic activity being increased after that or something like that.
Yes, absolutely. You can really see brain at work. So which areas are active when you do a certain task or you have a certain emotion even. This can also be used in diseases. For example, in Alzheimer's disease, it is clear that there are certain regions that are using less energy. One reason of this is that these neurons in these areas are dying, so they consume less energy, so you have a smaller signal. But what is interesting is that now there is evidence that areas that eventually will degenerate, where neurons will degenerate, already show some signals of decreased metabolism. So it's interesting to see that, there is a lot of developments now to try to use this as a kind of a prediction of how, if someone is at risk for Alzheimer's or another degenerative disease. The problem is that even if you can anticipate that potentially this person will develop Alzheimer's, you don't have much to offer today, and so it's a bit of a disappointment, of course.
Yeah, I saw your comment in the proceedings of the National Academy of Science about this, just about the metabolic activity, the imaging produced by the metabolic activity as a marker of. Can you tell us a little about?
Yes, this is a very interesting recent development made by colleagues at Washington University under the leadership of Mark Rakel, one of the pioneers of functional brain imaging. And what they saw is that in areas of the brain that are involved in learning, in particular in this case was motor learning, very subtle motor learning, there are metabolic changes that indicate that events related to what is called brain plasticity are taking place. So by looking at a certain metabolic profile in a given area in which is involved in learning, you can actually visualize, if you wish, the processes of learning, which areas are undergoing a certain type of learning. And as I said, this is a marker of neuronal plasticity. So in a nutshell, neuronal plasticity is a fundamental physiological process of the brain that is at the basis of learning. Definitely, neurons are connected through synapses, but these connections are not fixed once and forever, like you would have in a computer with a microchip which is printed and is printed once and forever, our connections are very dynamic. And for example, when a given neuronal network is involved in learning, the connections can actually become stronger. They can even become even more connections can happen in a given circuit because of learning. This is called neuronal plasticity, which is at the basis of learning. Well, the paper you're referring to is able in a way to visualize this process of plasticity.
Totally amazing. And what happened during the sleep with the brain energy? Is going down, or what happened?
Well, as you know, sleep, we have two major phases of sleep. One is called slow wave sleep, which is really a part of sleep, a period of sleep where indeed there is less metabolism. About the metabolism goes down by 30% more or less in the brain. So there is less energy consumed, if you wish. But then, during these periods of, let's call it rest or hypometabolism, there are suddenly periods of very high activity, electrical activity, but also metabolic activity. It's a paradox because people are sleeping deeply, but yet their brain activity is very high. It's called paradoxical sleep, or rapid eye movements, because the eyes move very quickly during this period. And it's also the period when we have these dreams, the most strange dreams that every one of us experiences. So in terms of metabolism, this period actually uses as much metabolism as when you're awake, and sometimes even more. So there is a paradox, essentially.
So that means that there is a circadian clock going on, working there, regulating in some way the brain energy, metabolism, up during the day, low during the night, or depending on the phase of the sleep?
Well, the connection between the circadian clock, indeed, as you mentioned, our brain has areas that actually synchronize the brain states with the light-dark cycle. And hopefully we are more or less synchronized. We tend to sleep when it's dark and to be awake when it's light. It helps social life and many other things, you know. For rodents, it's the other way around, by the way. Rats are very active during the dark, and they tend to be sleepy during the light phase. So, indeed, there is an overall synchronization of metabolism also with the light-dark cycle. But then what I described, these two phases of sleep are somehow independent. I mean, they just happen during the dark phase.
Can you tell us a little bit about IBRO, the main mission of IBRO, always concerning to the brain, concerning to supporting brain research and so on? So
yes, I mean, IBRO is really a quite unique organization because it's worldwide, and its mission is to support, facilitate, promote education and training, and somehow also research, but mostly education and training of young, mostly, neuroscientists worldwide. So it's an organization that is active not only in Europe and North America, as many organizations involved with science, but really it's worldwide. IBRO is organized in regions, so there is actually a Latin American region of IBRO, there is a North American, there is a European, there is a Africa region, there is Asian Pacific. So, and these regions have committees that identify the needs for training and education. So they are close to the field.
To the field in each region.
And they know the needs in every region. So the goal is really to promote neuroscience for young science.
But this is not the first time for you in Buenos Aires. No. Is that right? You have been here a couple of times. Why?
I was here a couple of times in another context, in a way. That was to promote two books. that I wrote with a colleague, psychoanalyst, François Ansermet, that were published originally in French. But then they were translated in Spanish, by a local publisher, an Argentinian publisher, Katz Editores. And they, the first one is called A cada cual su cerebro.
A cada cual su cerebro.
And the other one, Los enigmas del placer. And the message in both books is to see where there are potential intersections between neuroscience and psychoanalysis. And this is really a field that is completely on the side of my experimental work, but which I am actually very interested in.
To approach
maybe it goes to the original interest. I wanted to be a psychiatrist, and I ended up to be a neuroscientist, and I'm very happy like that. But I think I always kept an interest to the mind, the psychic life. And I became quite interested in the work of Freud. I think he was a neurologist. I would say he was a neuroscientist, really. And then when he saw that, the tools and the knowledge of the time in terms of brain function was somehow limited, then he developed a very, very insightful set of theory about.
Pierre, tell me the reason of your visit to Buenos Aires in this occasion.
Well, it's for the FALAN meeting, the second FALAN meeting, which is the Federation of Latin American Neuroscience Societies. And I am really pleased to be here and very impressed by the quality of the science that is presented through the program. I mean, really a very nice symposia, posters of high quality, and most of it, again, the nicest thing is to see young people around, and there are a lot of young Latin American neuroscientists, and it's really important to maintain this momentum, I think, in Latin American neuroscience, times are difficult in every country at the moment, but of course, maybe I'm a bit biased, but I think it's really important that support is maintained to our Latin American neuroscience with grants coming from governmental agencies. And OIBRO can bring its contribution in terms of training and education, and we do it really. We're extremely motivated because we see actually in 10 years where IBRO has really been involved very much in Latin America, we see, I think, that we hopefully had a
good progress.
And that we made a certain contribution to it, and of course,
for sure, yeah.
The national agencies and the national organization have done a lot, but
for
sure
IBRO
can
support a lot as well. Yeah, I'm very glad. What do you think about the future of neuroscience, and how do you see the field? How do you see the contribution of the neuroscientists trying to solve all the problems related to diseases, Alzheimer, Parkinson, and so on?
Yes, obviously I believe that there will be progress in the knowledge in neuroscience, and hopefully some breakthroughs that will help prevent or understand the mechanism and then eventually prevent and treat, in particular, neurodegenerative diseases. If I compare the knowledge that has been accumulated since when I started, it's just amazing.
Yeah.
But I still think, and this is a purely personal view, and I may be completely wrong, but I think we essentially, if we would define what is the global knowledge about the brain, how much do we know about, I would say 10%. So I think we have a lot to learn. But it doesn't mean that we should be, kind of depressed by the immensity of the task. We should just keep on going. I think some tangible progresses will be made in the short term by the interface with technology, with computer sciences, with nanotechnology, development of nanosensors, that will bring a lot of insights on human brain function and also rehabilitation possibly. So I think the field of neurotechnology, the broad field of neurotechnology, will be probably the one that brings on the short term most advances.
A lot of work to do. Tell us a little about your own experience, your own likes, and you like music, art.
Sure. Well, I like art, of course, and music. I don't practice. I'm not a musician. I play a little bit the flute, but
The flute,
better not to listen to me. And by the way, before I go to sleep, I tend to just go a few pages of catalogs from museum. I just look at these nice paintings, particularly from the Renaissance, Italian Renaissance, and somehow I
like it too.
I have a beneficial effect on it. And then I play. I used to be quite good, and less now because I have less time, but I play golf. I was actually in the Swiss national team, and that's a sport that requires a lot of brain activity. And I always say that if someone could find neurotechnological ways to improve golf, one would make a fortune, because there are 200 million people around the world who are just missing shots. And that could be very, very interesting. And I also like, and I'm very pleased to be here in Argentina, I like good wines.
Oh, good
and of
wines.
Course,
Me
here,
too. And the barbecue? What about the
barbecue
barbecue?
also, but good wines are special. And I'm very happy to be here in Argentina for this. I'm drinking a lot.
Exactly. Okay, Pierre, I have to say thank you so much for visiting us. It was a great pleasure to talk to you, and I hope to see you again soon.
Of course, I thank you very much for this conversation. I much enjoyed it.